So good day everyone. Today we will be discussing the reactions of alcohols and phenols. These compounds may seem similar, but their behavior varies in different ways. Throughout this discussion, we'll uncover how they transform under different conditions and why these reactions matter. So let's get started. So alcohols are compounds where the hydroxyl group is attached to a carbon atom. The general formula is the ROH, where R represents an alkyl group. So a common example is ethanol, which consists of two carbon chain with a hydroxyl group attached. The structural diagram on the right shows ethanol's molecular structure, where carbon forms single bonds with hydrogen and another carbon. So on the other hand, phenols are a special class of compounds where the hydroxyl group is directly attached to an aromatic benzene ring. The general formula is AROH, where AR represents an aryl group. We have here the structures of a phenol, which consists of a benzene ring bonded to an hydroxyl group, as shown in the structural diagram. Now that we understand the basic structures of alcohols and phenols, let's take a closer look at how they compare in terms of their chemical properties and reactions. So this table highlights the key differences between alcohols and phenols. First, in terms of functional groups, alcohols have their hydroxyl group attached to an aliphatic carbon, while phenols have it directly bonded to an aromatic benzene ring. So these structural differences affect their acidity, as phenols are generally stronger acids than alcohols due to resonance stabilization. So in reacting with sodium metal, both alcohols and phenols release hydrogen gas, but alcohols form alkoxides while phenols form phenoxides. So another key distinction is in electrophilic substitution reactions. Alcohol do not undergo these reactions, whereas phenols do, so typically at the ortho and para positions of the benzene ring. So in esterifications, alcohols readily react with carboxylic acids to form esters, whereas phenols are less reactive in this process due to the resonance stability of the benzene ring. So lastly, their common uses also differ. Alcohols are widely used as solvents, fuels, and disinfectants, while phenols are found in antiseptics, pharmaceuticals, and plastics. Now that we've compared alcohols and phenols, let's focus on chemical behavior of alcohols. So before diving into specific reactions of alcohols, let's get first an overview of the type of transformations they undergo. So alcohols are highly versatile compounds that can participate in various chemical reactions, depending on the conditions and reagents used. In the next slides, we will explore the key reactions of alcohols, including oxidation, dehydration, substitution, esterification, and their reactions with sodium metal. Understanding this fundamental process will help us predict how alcohols behave in different chemical environments. So one of the most reactions of alcohol is oxidation, depending on whether the alcohol is primary, secondary, or tertiary. Oxidation leads to different products. So let's break down how oxidation affects each type of alcohol. In primary alcohols, these undergo oxidations in two steps. First, they are oxidized into aldehydes, and with further oxidation, they form carboxylic acids. For example, ethanol first converts into acetaldehyde and then into acetic acid when an oxidation agent is present. So in secondary alcohols, they are oxidized to ketones. Unlike primary alcohols, they do not oxidize further into carboxylic acid. For example, a propanol is oxidized to propane, or otherwise called as our acetone. So in tertiary alcohols, these do not undergo oxidation because there is no hydrogen atom attached to the carbon bearing the hydroxyl group. So since oxidation requires the removal of hydrogen, tertiary alcohols remained unchanged under typical oxidation conditions. Now that we understand how oxidation works, let's move on to another important reactions of alcohols, the dehydration. So this reaction plays a key role in converting alcohols into alkenes, which are useful in many industrial and synthetic processes. So let's take a closer look at how this works. So, dehydration of alcohols is a reaction where an alcohol loses a water molecule to form an alkene. So, from the word itself, dehydration. So, this process requires a strong acid catalyst such as concentrated sulfuric acid or aluminum oxide and typically occurs at high temperature around 180 degrees centigrade. So, the reaction follows two mechanisms, the E1 and the E2. So, E1 is otherwise known as our elimination unimolecular. So, it occurs in tertiary and secondary alcohols where the formation of a carbocation intermediate plays a crucial role. So, in E2 or elimination bimolecular, this happens in primary alcohols where the elimination of water occurs in a single step without forming a carbocation. So, let's take a look in the structural diagram. During dehydration, a molecule of water is eliminated from an alcohol structure. Sulfuric acid acts as the catalyst for this reaction and is placed above the reaction arrow along with a specified condition of 180 degrees centigrade, which facilitate dehydration. So when water is removed, a carbon-carbon double bond forms because carbon must maintain 4 bonds. To compensate for the loss of the hydroxyl and hydrogen groups, a double bond forms between two carbon atoms. As a result, the alcohol is converted into an alkene, with water as a byproduct. So this reaction is important in organic synthesis, especially in producing alkenes, which serves as building blocks for many industrial chemicals and polymers.
Substitution reaction of alcohols. Alcohols undergo substitution reactions where the hydroxyl group is replaced by a halide ion. However, since OH is a poor leaving group, it is first modified to improve reactivity. SN1 mechanism or tertiary and some secondary alcohols. The SN1 reaction follows a two-step mechanism and occurs mainly in tertiary alcohols due to the stability of the carbocation intermediate. 1. Pronation. The alcohols react with a strong acid like hydrochloric acid and HBr, converting to the OH group into water, which is a better leaving group. Number 2 is carbocation formation. The water molecule leaves forming a carbocation. This is the slowest step and determines the reaction rate. 3 is nucleophilic attack. The halide ion then attaches to the positively charged carbon, forming an alkyl halide. Example: the tertiary butanol reacts with hydrochloric acid to form tertiary butyl chloride in water. Since the reaction proceeds through a carbocation, rearrangements may occur if a more stable carbocation can form. SN2 mechanism, primary and some secondary alcohols. The SN2 reaction is a one-step process that occurs primary and alcohols due to the minimal steric hindrance. The nucleophile directly attacks the carbon, displacing the OH group in a backside attack mechanism. This causes an inversion of configuration. Example: ethanol reacts with hydrobromic acid to form ethyl bromide in water. Since the reaction is concerted, no carbocation forms, making it faster for primary alcohols. Common reagent for substitution is thionyl chloride or SOCl2, converts alcohols into alkyl halides, often in the presence of base like pyridine. Next is phosphorus tribromide or PBr3, used to convert alcohols to alkyl bromides with better control over reaction conditions. Esterification of alcohols. The Fischer esterification is a reaction where alcohols and carboxylic acid form esters in the presence of a strong acid catalyst like sulfuric acid or H2SO4. Reaction example: ethanol reacts with acetic acid to form ethyl acetate in water. This reaction is reversible, so excess reactants or removal of water helps drive the reaction forward. Esters are widely used in the fragrance and flavor industry, in polyester production for textile and packaging, and as key components of triglycerides and fats.
The reaction of alcohols with sodium metal or Na. So why do alcohol react with sodium? Although alcohol are not very acidic, they can still donate a proton or H plus from their hydroxyl group. When reacting with highly reactive metals like sodium, so when alcohol react with sodium metal, the hydrogen from the hydroxyl group is removed. And then a sodium alkoxide is formed. Then lastly, hydrogen gas is released as bubbles. So example, we have here the ethanol reacting with sodium. So one of the most well-known alcohols is the ethanol. Reacts with sodium as follow. So I'll also drop the formula below. So I'll continue with the reaction. So ethanol, the alcohol. So we have here the ethanol, which is our alcohol. Then the sodium, which is the reactive metal. And then the sodium ethoxide, the product, which is a strong base. Then lastly, we have here the hydrogen gas, released as bubble, just like what I've said earlier. So what do we observe during this reaction? First is the bubble of hydrogen gas. Mo-form siya and then showing that the gas is being released. Then sodium metal dissolves in the alcohol. And then lastly is the reaction produces as a colorless solution of sodium ethoxide, which is a strong base used in organic synthesis. Then why do some alcohol react faster than others? The reactivity of alcohols with sodium depends on their structure. Primary alcohols like ethanol react faster because they have the least steric hindrance. Then the secondary alcohol like isopropanol react moderately. And then the tertiary alcohol like terbutanol react very slowly or sometimes not at all, because the bulky groups around the hydroxyl make it difficult for sodium to react. Then here are the key differences between alcohol and phenols in this reaction. Alcohol reacts slowly with sodium because they are weak in acid. So the strength of the acid determines how easily hydrogen gas is released. So let's move on to the reaction of phenols. So what are phenols? Phenols are similar to alcohol but have one major difference. The hydroxyl group is directly attached to a benzene ring. This makes them more acidic than alcohol and also changes their chemical properties. We also have here the electrophilic substitution reactions of phenols. So why do phenols undergo electrophilic substitution? The hydroxyl group in phenol makes benzene ring more reactive, means that the electrophiles or electron-seeking species attack the ring at the ortho or the para positions. Ortho, we all have here the 2 and the para 4. And then first is the nitration of phenol reaction with nitric acid. So when phenol reacts with dilute nitric acid, a nitration reaction occurs forming 2 nitrophenol and 4 nitrophenol. Then here we can observe that yellow-colored products are formed if concentrated nitric acid is used. Picric acid, or also known as trinitrophenol, is formed, which is very exclusive. Then we also have here the halogenation of phenol reaction with bromine. So when phenol is treated with bromine water, a halogenation reaction occurs forming 2,4,6 tribromophenol, which is a white precipitate. And then the observation that you can see here is that the orange or orange-brown color of bromine water disappears, and then a white precipitate of tribromophenol forms. So last, we have here the final summary of key points. So alcohol and phenols react with sodium metal, producing hydrogen gas and forming alkoxide or phenoxide ions. Phenols react faster with sodium than alcohols because they are more acidic, and phenols undergo
electrophilic substitution of ortho and para positions. The nitration of phenols forms. And nitration of phenol forms 2-nitrophenol and 4-nitrophenol. And then last we have here the halogenation phenol with bromine produces the 2,4,6 tribromophenol as a white precipitate. Phenols undergo electrophilic substitution, making them highly reactive in organic chemistry.
This video will delve into the world of phenol oxidation, exploring the mechanism, importance, and application of this reaction. From the synthesis of quinones to the whole biological system, we'll cover it all. We proceed to hydroquinone to benzoquinone. Step 1. Hydroquinone structure. Hydroquinone has 2 hydroxyl groups attached to a benzene ring. Step 2. Oxidation initiation. The oxidation reaction is initiated by the addition of an oxidizing agent represented by oxygen. This agent can be chemical oxidants such as a potassium permanganate or chromium trioxide. Next is step 3, electron transfer. The oxidizing agent accepts electrons from the hydroquinone molecule, initiating the oxidation reaction. This electron transfer process is facilitated by the presence of the hydroxyl groups. Step 4, formation of benzoquinone. As the oxidation reaction proceeds, the hydroquinone molecule loses 2 electrons and 2 hydrogen atoms, resulting in the formation of benzoquinone. Step 5, water formation. The two hydrogen atoms lose during oxidation reaction to combine with an oxygen atom to form a water molecule, which is released as a byproduct. Step 6, final products. The final products of the reaction are benzoquinone and water. This oxidation reaction is an important to process in various biological and industrial applications, including the synthesis of quinones and the degradation of organic pollutants. Here's a step-by-step explanation of the Williamson ether synthesis for each example. Synthesis of anisole. Starting materials, phenol and methyl iodide are the starting materials. Next is deprotonation. Phenol is deprotonated by a base to form phenoxide ion. So, on 3, nucleophilic attack. Phenoxide ion attacks the methyl iodide, leading to the formation of new bond. Next is elimination of iodide. The iodide ion is eliminated, leaving behind the anisole product.